A uniform electric field is a field where the force on a charged particle is the same in both magnitude and direction at every point. This is commonly illustrated between two large, flat, parallel plates that are oppositely charged, creating evenly spaced field lines pointing straight from the positive plate to the negative plate. The field lines points directly toward the negative plate, and the electric field lines are parallel and evenly spaced, showing that the field strength is constant throughout this region. The electric field strength is calculated by dividing the voltage difference by this separation. This setup helps us understand how electric fields behave in a controlled and simplified way. Here, we can see that the electric field strength is defined as the potential difference divided by the distance between the 2 points. This means that the field strength depends on how much voltage is applied and how far apart the two charged plates are. The parallel plate capacitor consists of two conductive plates separated by an insulating material. It stores electrical energy by holding opposite charges on each plate, one positive and one negative. The arrows between the plates represent the electric field created by these opposite charges, which is what allows the capacitor to hold energy. Capacitance depends on the area of the plates, which is represented here by A, and the distance between them, labeled D. The constant Epsilon0 stands for the permittivity of free space, which affects how electric fields behave between the plates. Essentially, capacitance increases as the plate area gets larger or the distance between the plates becomes smaller. This relationship helps us understand how to design capacitors for different applications by adjusting these factors. Now, let's look at how we can push the limits of capacitance without changing the physical size of the capacitor. One effective way is by inserting a dielectric material, which is an insulator, between the capacitor plates. This material is characterized by its relative permeability, represented as epsilon(r). The presence of this dielectric increases the overall capacitance, according to the formula shown, where capacitance is proportional to this relative permeability. On the left, you see a capacitor with just a vacuum or air gap between the plates, with the electric field lines drawn in blue. On the right, the same capacitor includes a dielectric material, which leads to more electric field lines for the same charge, indicating an increase in capacitance. Polar molecules and dielectrics respond to an external electric field by aligning themselves with it. When the field is off, these molecules are randomly oriented, but once the field is on, they rotate and align in a way that creates an opposing electric field. This opposing field reduces the net field strength between the plates, which means the capacitor can store more charge at the same voltage, improving its overall performance.